I did something impossible on consumer hardware, and now I'm going to teach you how. One of the biggest bottlenecks for local inference has been the inability to store large context without using up huge amounts of memory. You would literally need a whole GPU just for the context alone. But I've solved that. The KV cache alone at 72,000 context would need 23 gigabytes of memory, more than the free VRAM on both cards combined after loading the model. But I got it working, and I'm going to show you exactly how. This is TurboQuant, a KV cache compression algorithm from Google that promises 4.57 times compression with near lossless quality. I took their paper, implemented it in CUDA inside llama.cpp, and pushed it through 3 phases of engineering until it actually worked at full context on real hardware. Everyone in the local LLM community obsesses over tokens per second, but here's what actually matters: context length. TPS is a comfort metric. Context length is the capability ceiling. It's the difference between a chatbot that forgets what you said 3 messages ago and an agent that can reason over your entire code base. The bottleneck isn't the model weights. A 4-bit quantized 70 billion model fits in about 40 gigabytes. Tight on two 3090s, but it fits. The bottleneck is the KV cache. Every single token you generate stores key and value vectors across all 80 layers, 8 KV heads, 128 dimensions. That's 0.31 megabytes per token. At 17K context, that's 5 gigabytes. At 72K, 23 gigabytes. There's just no room. So the question becomes, can we compress the KV cache without destroying the model's ability to reason? Google's TurboQuant paper from ICLR 2026 says yes. The core idea is elegant. Take a KV cache vector, normalize it to unit length, saving the norm separately. Then rotate it using a Walsh-Hadamard transform that's a fast mathematical operation that spreads the information evenly across all dimensions. Why does this help? Because after rotation, every coordinate in the vector follows approximately the same Gaussian distribution. That means you can use a single optimal quantizer for all of them. No calibration data, no per-channel tuning. Just one set of 8 Lloyd max centroids that work everywhere. You quantize each value to 3 bits, pack them efficiently, and then store a scale factor. So, total you have 14 bytes per 32 values. That's 3.5 bits per value instead of 16, a 4.5x compression ratio. But here's the thing, I didn't start from zero. A community developer called Unix SysDev had an initial implementation in llama.cpp, but it had 2 problems. It only used 2-bit quantization with 4 centroids, and the output was garbage. The model just repeated the prompt endlessly. I traced the bug to a single line of code. The original code multiplied by 1 over 32, assuming both sides normalized. The fix was changing it to 1 over root 32, one constant. That's the difference between garbage output and coherent text. Then I upgraded from 2-bit to 3-bit quantization, from centroids to 8. Modified the CUDA kernels for quantization, dequantization, and the dot product. After that, K-only compression worked beautifully. Generation speed within 7% of baseline. K-cache was the easy part. V-cache nearly broke me. The first problem, llama.cpp has a deadlock. The TurboQuant K-cache forces flash attention off because the flash kernel can't do the query-side Walsh-Hadamard transform, but quantized V-cache types require flash attention on because the flash kernel is what reads quantized V directly. K needs flash off, V needs flash on. Both can't be true. My solution was to bypass flash attention entirely for V, dequantize the V cache to full precision before the standard matrix multiplication. But that exposed problem number 2. GGML stores the vcache transposed for efficient matrix operations. Transposed storage writes one element at a time, but TurboQuant is a block quantized format. It needs groups of 32 elements. 1 mod 32 does not equal 0. The CUDA kernel crashes with an assertion failure. The fix is to store v non-transposed when it's quantized, then explicitly transpose after dequantization in the attention graph. The third problem, I dequantized v to float 16 to save memory. It works perfectly on GPU, but then it crashed on CPU. It turns out llama.cpp's CPU backend only supports dequantizing to float 32, not float 16. And with multi-GPU pipeline parallelism, some layers inevitably end up on CPU host memory. So switch to float 32 intermediate and everything works. Phase 2 result, full 4.5 times compression, coherent output, 9 tokens per second, but maximum context was only 16,000. Here's the cruel part. I compressed the KV cache by 4.57 times, and the context length barely improved. Why? Well, without flash attention, the attention computation itself requires an n squared memory matrix. At 16K context, that's 2.3 gigabytes of compute buffers per GPU. At 20K, it explodes to 16 gigabytes. The KV cache was tiny, thanks to compression, but the attention math was eating up all the VRAM. So I had solved the storage problem and run straight into the computation problem. Now this is where it gets good. This is the breakthrough. I was staring at the dequantization code and I realized something. When you dequantize TurboQuant, the code runs the full inverse Walsh-Hadamard transform. It restores the values back to their original unrotated space, approximately because of quantization error, but close enough. If dequantized k approximately equals the original k, then you don't need the query side WHT at all. Standard queue times k transpose attention just works, which means standard flash attention just works. The entire phase 3 implementation was 2 code changes. Remove the line that forces flash attention off the TurboQuant. Add dequantization of k and v before the flash attention kernel, and then the KV cache stays compressed at 4.57 times in VRAM. When the model needs to compute attention, it reads the compressed cache, dequantizes on the fly, and feeds the result into the existing flash attention infrastructure. Flash attention tiles the computation internally, so memory usage becomes effectively constant regardless of context length. The result? We get 72,000 context, which is really powerful for local inference. Actually, it can even go to 80,000 if you push it to free VRAM, so 72K with comfortable headroom. And if you want to change to a smaller model like Quant 32 billion, you can even push it to 131,000 context, basically maximum context, and still have a lot of room to spare. So 5 times the context of phase 2 using the exact same compression. Now let me give you the real numbers. Wikitext 2 perplexity at 72K context on Llama 3.3 70B. Baseline with float 16 KV cache is 4.09. Full K and V TurboQuant compression 4.4. That's a 7.6% increase. For context, Q4 model weight quantization itself typically adds 2 to 7%. So we're in the same ballpark, a measurable but practical trade-off. K-only compression came in at 6.6%, close to the full compression number, which tells us most of the degradation is coming from the quantization itself, not specifically from V compression. The generation speed at 72K context is 5.1 tokens per second. Not fast, but the alternative was 0 tokens per second because you literally could not fit 72K context before. So let me put this into perspective. Without TurboQuant, the KV cache for 72K context would need 23 gigabytes. The model already uses 40 gigabytes across both of my GPUs. There is physically no room. So with TurboQuant, that's 23 gigabytes. That 23 gigabytes becomes 5 gigabytes. The model fits, the KV cache fits, flash attention handles the computation, and you get the full context window of the model on hardware that costs under $2,000. This isn't a marginal improvement. This is a capability shift that didn't exist before on this hardware class. Now to close off the video, the paper and the code and the benchmarks are all public. The link to the repo and the paper is in the description. If you're running multi-GPU inference on consumer hardware and context length matters to you, then try it. But I want to be clear about what I built and what I built on. Google wrote the TurboQuant algorithm. Unix System figured out the query-side WHT architecture that makes it work on multi-GPU. I fixed the normalization bug, upgraded to 3-bit quantization, solved V-cache compression, and figured out that graph-side dequantization re-enables flash attention for long context. Each piece matters, and I'm grateful to the people who laid the groundwork. The code is on GitHub. The paper explains every engineering decision. If you want to push this further, a fused flash attention kernel with in-kernel WHT would recover the speed gap. I'd love to see it. And there's also the potential that we could apply TurboQuant to the model weight quantization itself for even more benefits. Thanks for watching, and please like, comment, and subscribe to my channel.